Okay, so we're going to just kind of quickly go through the part here about balancing and the law of conservation of mass, because we've already talked about how you balance a chemical reaction and that it's important you have the same amount of everything on both sides, because that means you didn't create matter or destroy matter, which is important. That's the law of conservation of mass. Okay, but what we also want to look at today is if I'm only given the reactants in an equation, can I figure out what the products are going to be and kind of the steps that you would follow in order to be able to accomplish that? Right, so we're going to understand that the amount of atoms on the reactant side of an equation must be the same as it is on the product side. That's what balancing is all about. Okay, learn to use coefficients. That's the balancing numbers that we've been putting in to balance chemical equations. Okay, basically that's saying if I have a reaction, okay, like I don't know, let's say okay, I can't just say, oh, well, I've got 2 chlorines over here, so I'll just make 2 over here. Okay, that's what this point is saying. I can't change the compound. This changes the compound. All I can do is change how much of that compound there would be. Okay, and then go back over here and make sure that I've got it balanced on both sides. Okay, so that's the important thing there. How do we decide what small numbers should be in one of these reactions? Yeah, either we've dropped and swapped them because they were ionic, or we read them from the name of a molecular compound from the prefixes, okay? Or it's a special element. Okay, if it's oxygen or nitrogen or hydrogen or something like that, we know it comes as a 2, or phosphorus as a 4, or sulfur as an 8. That's where those numbers come from. I don't use those numbers to balance because I can't change them. Okay. All right, and then obviously understand the law of conservation of mass. You can't create matter, you can't destroy it. Okay. All right, so the law of conservation of mass says that mass is always conserved in a chemical reaction, in any kind of reaction, actually. Okay, even in a nuclear reaction, okay, mass is still conserved, right? The same number of particles exist before and after, okay, any kind of reaction. There's no way to destroy or annihilate matter completely. Okay, even a black hole is not making matter go away, right? It's taking more and more in and adding to its own mass. Okay, but it's just the mass is always there. Right? Since all matter has mass, okay, the mass of the reactants must equal the mass of the product. So in this reaction here, okay, there's 4 hydrogen atoms on this side. There are 4 hydrogen atoms on the other side. So the amount of hydrogen is equal. There are 2 oxygen atoms and 2 oxygen atoms, so the mass of everything on both sides is the same. This becomes really important when you get to Chem 20 and you start doing what's called stoichiometry. Okay, in stoichiometry, you take a balanced chemical reaction like this one, and if you know you have a certain amount of hydrogen over here, you have to calculate the mass of water it would produce. Okay, that's stoichiometry. You start doing that in Chem 20. Okay? But it only works if you balance the equation right. If you don't balance the equation right, you won't calculate the mass because you'll say you had more or less than you were supposed to have. Okay, so that's why we concentrate on the balancing part in Science 10. So you do that easily so you can get to the stoichiometry part in 20. All right, so in any physical or chemical change, the total mass of starting materials has to equal the total mass of product materials. That's why we balance everything. Which one, B, C, or D, is showing the law of conservation of mass followed? D? Okay, so we got 2, 4, 6, 8, 10 red ones, 2, 4, 6, 8, 10 red ones. Okay, and we've got 3, 6, 8 of the yellow, so 3, 6, and 8. Yeah. Okay, so D is showing that the law of conservation of mass has been conserved, right? Because in this one here, there's less yellow than there was in the first one, and in here there's just less of everything, okay, than in the first one. All right, so balancing, like I said, we've already gone over the balancing steps. This is just so that you've got the notes on it, okay? So the first step is you write the chemical formula for each reactant, and if you have it, each product, okay? And you don't have to include the state of matter. Is that still in your notes package, including the state of matter? It is? Cross it off. You guys in Science 10 don't have to write the state of matter. I thought I took that out of the package. The S, yeah, the S or the AQ or yeah. Okay, step 2, try balancing the atom or ion present in the greatest number, except with what kind of reactions? Combustion, which we balance alphabetically. Okay, use coefficients, that's numbers in front, to get equal numbers of atoms on both sides. Repeat step 2 to balance each of the remaining atoms. Okay, and then lastly, check again. That's a step people often skip. Okay, sometimes you think you've got it balanced, but the last number you wrote threw something off. Okay, so it's always good once you think you have it balanced to double check everything at the end just to make sure. Okay, so in this example here, okay, this is actually looking at kind of the first prediction thing that we'll look at. So we'll actually kind of set it up like this. So in this reaction, it says a piece of copper wire is immersed in silver nitrate. Okay, and it actually said in the notes a single replacement reaction occurs. If I was giving this to you, I wouldn't even say that. I would just give you this. A piece of copper wire is immersed in silver nitrate. Okay, so what are the reactants for this compound look like? Well, they look like copper and silver nitrate. I know you've got the answers in front of you. That's why I'm just going to move through it here. All right, so this is a element reacting with a compound, which is a single replacement reaction. Okay, so we have to be able to recognize the chemical reactions, the 5 we went over, by just looking at the reactants. Okay, they all have a different pattern. If this was a synthesis reaction, there would be 2 elements here. If it was a decomposition reaction, there'd be 1 compound here. If it's a combustion reaction, there's carbon, hydrogen, and oxygen. Okay, if it's double replacement, there's 2 ionic compounds. We can tell them all just by looking at how they start. Okay, now in a single replacement reaction, something has to replace something else. Copper is a metal, so who is it going to replace? It's going to replace silver. Okay, so that means that on this side, copper is going to end up with nitrate, and silver is going to end up alone. Okay, I have a bit of an issue here. Copper has more than 1 possible charge, and they never told me which one I'm using. I use the most common one. The most common one is the first one listed on the left. Okay, so on your periodic table, that should be Cu, that should be 2+, right? Okay, so if you're not told, and in this case you're not, because copper, when it's an element, doesn't have a charge. Okay, so there would have been no way to know. Okay, then we say, okay, copper is 2+, nitrate is 1-, so we drop and swap. We'll need brackets. Okay, and silver isn't special. That's not to hurt its feelings, but it doesn't come with a 2 or a 4 or an 8. Okay, so we just leave it like that. And now we look to balance the whole reaction. All right, so the only thing right now that's out of balance is nitrate. There's 2 on the product side, but there's only 1 over here on the reactant side. So we put a 2 there. Okay, that gives me 2 silvers. So I've got to go back over here and make sure I have 2 silvers. I have 1 copper and 1 copper on each side. Okay, now last step, supposed to double check. 1 and 1, 2 and 2, 2 and 2. Good. Okay, got a question? That is the reaction where the silver would coat the copper. Yes, it would. It's called plating. It would plate out and just kind of form there. Yeah. All right. So does that process kind of make sense? Okay. As long as you can identify what reaction type is taking place, predicting the products is actually pretty straightforward because we know every reaction we've gone over has a specific pattern. Okay. Check it. Well, no, because I had to create this compound, right? When I was making this reaction up, I just knew copper and nitrate were going together, right? I didn't know, like nitrate's charge is always -1. I didn't know to put a 2 there until I figured out that copper's most common charge is 2. Yeah. Okay, let's try, oh, sorry, question, Jake? We can't assume that because +1 copper is actually quite rare, right? The 2+ is very common, right? And that's the way your periodic table is set up. 1 charge is far more common than the other. No, because it doesn't have a charge here, right? Elements don't have a charge; they have the same number of electrons and protons. That's why why we have to have that little trick. Is there was no way for me to know if it was 1 or 2, so I just have to assume it's the most common one and go with that. Okay. Now, if it had said, if I had started out with copper nitrate over here, it would have said copper 2 nitrate, and I would have known. Okay, but what you mean, like a Roman numeral? No, again, I only put that there if it has that charge. This doesn't have a charge, it's an element. Okay, and I would only put it in the name anyway. We never put the Roman numerals in the formula equation. Okay, they only ever go in the name. All right, let's try a different one here. Let's try, I don't even know if this compound exists, but we'll try it. Okay, what kind of reaction is that? Simple decomposition, right? It's the only reaction type we have that starts out with only one reactant. Okay, so in a simple decomposition reaction, this stuff is going to split. Okay, and we're going to get some phosphorus and we're going to get some oxygen. Okay, so it was easy to figure out what the products were, but now what do I have to do with them? Before I can balance the equation, what do I have to check for? Right, I got to check for special elements. In this case, there are 2. Both of them are special elements. Phosphorus comes as a 4 and oxygen comes as a 2. Okay. I don't know if it'll be that hard. Okay. I got 5 oxygen over here, right? Okay, and I got 2 over there. Lowest common multiple is 10, yeah? I just balanced my phosphorus. Now my oxygen works too, right? All right. Okay, try this one. What kind of reaction is that? Okay. What are the products of a combustion reaction always? Water and CO2. Okay. So this one's not, this one you don't really have to think about, you just have to memorize. Okay. Products of a combustion reaction are always carbon dioxide and water. There's not any really prediction there. It's just that's what it is. Yes. Well, right now I would do it once I have the whole reaction written out. Yeah. Okay, so remember we got 2 special balancing rules. Okay, we've got to balance alphabetically, and we have the rule of 2. Does this need the rule of 2? Yes, 4 is an even number. Okay, 2 times 4 is 8. 8. 2 times 10 is 20. 10 times 2 is 20. 8 times 2 oxygens is 16, plus 10 more in the water is 26 oxygens. 13 times 2 is 26. Okay. All right, so is this prediction as hard as maybe we thought yesterday? Okay. Now when you look at that reaction lab and you're looking at those reactions, it's not going to be nearly as kind of intimidating as it might have looked like yesterday. All right, let's try a different one here. Let's try, that's what I was going to do. All right, my reactants are both ionic compounds. So this is a double replacement reaction. In a double replacement reaction, what do we do with the metals? Switch them. Okay, so that means iron is going to end up with bromine and magnesium is going to end up with chlorine. All right, what do I need to do to both of those compounds? Drop and swap them. They're both ionic. Okay, what charge did iron have over here? 3. Should it have 3 over there? Yes. Okay, I can't change the type of iron I have. If I had iron 3 on this side, I have iron 3 over here. Because I did this, right? Chlorine's a -1, so yeah. Okay, so that's going to be FeBr3 then. Okay, and this is a 2+, and this is a 1-, so it'll be MgCl2. Okay? And you can Guys, I mean, that pattern kind of shows up a lot in double replacement reactions. Okay. Now, I need to balance this whole thing. All right. So on this side, I've got 3 chlorines. On that side, 2. Lowest common multiple. Okay. So 2 here and a 3 here makes my chlorine 6 on both sides. That gives me 3 magnesium. So I got to come back over here and make sure I have 3 magnesium. That gives me 6 bromines. Now my bromines and my irons are balanced. 2, 3, 2, 3. Okay. As hard as you thought? It's really not a lot different than what we've been doing. It's just now you have to write the products in instead of being given them. Okay, but the products are always pretty obvious. No, well, it does, as long as you switch the non-metals or switch the metals, the end result's the same. Yeah. Yeah, it doesn't, in actual fact, it doesn't matter what order I write the products in. I could have written the magnesium compound first and the iron compound second. There's no rule on what order. Yeah. Okay. Okay. I want you guys to try those 4. Okay, so let's have a look at number 1 here. So I've got calcium reacting with oxygen. 2 elements are reacting, so that's a synthesis reaction. So what am I going to get on the other side? Yeah, I'm going to get a single compound. In this case, it's going to be calcium oxide. This is a -2. This is a +2. So that compound is already swapped and dropped correctly as CaO. Now I just need to balance the reaction. I got 2 here. Now I've got 2 there. A 2 here will take care of everything. Okay. How many people are done number 2? Okay, let's have a look at that one as well. All right, so we got what kind of reaction going on here? Decomposition. All right, so that means I'm going to get magnesium and sulfur. What do I need to check for? Special elements, right? Sulfur is the most special of the special elements. Okay, comes as an 8. So I would say that's probably what I got to start with. I need an 8 over here. That gives me 8 magnesiums, so an 8 right there. Okay. All right, how about number 3? How many people have done 3? Okay, I'll give you 1 more minute on number 3. Okay, so number 3, what kind of reaction? Combustion. What are always the products of combustion? CO2 and water. All right. Do I need to apply the rule of 2 to this one? No, it's got an odd number. All right, so I'm going to put 3 over here. I've got 8 hydrogens. Now I've got 8 hydrogens over there. I have 6 oxygens in the carbon dioxide, 4 more in the water, for a total of 10. Okay. What did I do? Yeah, you got to balance it alphabetically. If you don't balance a combustion reaction alphabetically, it's going to really be a nightmare. Because it's going to be carbon, hydrogen, and oxygen. Always. Always. Yeah.
Is oxygen always by itself?
In a combustion reaction, yes. Yeah. So guys, the question was, is oxygen always by itself in a combustion reaction? The answer is yes. Okay, we need free oxygen in order for this stuff to burn, right? Right, if there's an even number of carbons, I apply the rule of 2 and put a 2 here. If it's an odd number, then I don't need to. It just works out with an odd number, but with an even number, you get a decimal here for oxygen, which we can't have. Okay, let's look at the last one. Let's look at number 4 here. All right, so we got HCl reacting with NaOH. So we got 2 ionic compounds, so this is a double replacement reaction. All right, so both metals get new partners. All right, that means hydrogen ends up with hydroxide and sodium ends up with chlorine. And again, the order in which you write this doesn't matter. Okay, I could have written the NaCl first and the HOH second. That makes no difference. Okay, all right. There are no small numbers in this reaction, so it's already balanced. Okay, don't have to do anything else. This is dropped and swapped correctly. 1 and 1, 1 and 1. Okay, so we're all good there. Yes, acid and base reaction always gives you a salt of some kind and water, yes. All right, now I'm going to give you one here because this is a trick I like to play on a quiz.
What happens if you don't have any metals? If you get like a 2?
Okay, you would have to have ionic compounds for this to be a double replacement reaction. Replacement reactions only occur with ionic compounds. Okay, the only reactions you would get molecular compounds in are obviously combustion, and you can get them in synthesis and decomp. In fact, decomp reactions are often starting out with a molecular compound. Okay, with synthesis reactions, I typically don't have it make a molecular compound because it's hard for you to decide how many of each thing there should be because you can't drop and swap, right? You'd have to guess. So, all right, so case in point here, this is something I often do on quizzes to try and see how many people are paying attention. I would say something like this. Okay. All right, I'm going to give you a minute or two on that. Okay, so the purpose of me showing you this example, is to illustrate a conclusion we sometimes draw without thinking. What kind of reaction is this? It's a synthesis reaction, right? So these two elements should go together. Here's what a lot of people do. What kind of compound is this going to make when it goes together? What gets listed first in an ionic compound? Metal. Okay, common, but it's a common mistake. Okay, if I do that in an average Science 10 class, I will get 25 to 30% of people to write it that way. Because we just, oh, well, that's the order it's in over here. And it's really just a naming thing, right? It's a formula thing, okay? But I'll catch a lot of people with that simple trick, okay? So I would have to write it like this because it's going to be an ionic compound that I will have to drop and swap. This is a +1 and a -3, so it's K3N on this side. And now I can balance the reaction, right? So I go back over here. I've got 2 nitrogens. I don't want to balance the potassium first because it's not going to work out, okay? And then a 6 here, and now everything's good. Okay, but it's just one of those simple tricks that checks not so much whether you can do the reaction as to whether you remember how to write the formula for an ionic compound. Okay. Because if I put a 3 here, that won't balance my nitrogens, right? There's only 1 on this side. Okay, let's start it over again so you can see, okay? If I leave it like this and I just say, oh, well, I'm going to put a 3 here, that only balances my potassium. I have 2 nitrogen over here and only 1 over here. Because this is a molecule made of 2 nitrogen atoms. This is a molecule that only has 1 nitrogen atom in it. Therefore, I need 2 of those molecules to account for the 2 nitrogen atoms I have over here. Okay, and then I need 6 of these. Okay, we just got to look at the numbers. I got 2 nitrogens here, and now I have 2 nitrogens over here. If I don't have a number beside this, there's only 1. Right? And on this side, there are 2. Okay, so the first step in predicting the products of a compound is to write out the reactants. Swap and drop any ionic compounds and look for special elements that need numbers beside them, because you'll be given a prediction question, you'll be given in words. Okay, it would be like the example I did with the copper wire and the silver nitrate. Okay, if there are 2 elements, then you follow this. It's a synthesis reaction. Okay, we put the elements together into a compound, metal and non-metal, like sodium chloride, and then balance the whole reaction. Okay, if our reactant is 1 compound, then it's a decomposition reaction. Right, we split the compound and write the elements separately, and we check for special molecular elements, nitrogen, hydrogen, oxygen, whatever, and then we balance the reaction. Okay, if our reactants are carbon, hydrogen, and oxygen, and I've just put in here like CNHY, because those could be any number, okay? There could be any number of carbons or hydrogens, okay? Then it's a combustion reaction, okay? Always have the products CO2 and water. We balance in alphabetical order, okay? If we have an even number of carbon atoms, we put a 2 coefficient to begin and balance the reaction, okay? If our reactants are 1 element and 1 compound, okay, like this one here, calcium plus copper sulfate, that's a single replacement reaction. We look at the lone element and identify whether it's a metal or a non-metal. Okay, then use it to replace its counterpart in the ionic compound. So if it's a nonmetal, it swaps out for the nonmetal. Okay, and then we swap and drop our new ionic compound on the product side. We will check for any special elements because we're going to produce an element there by itself. Could be a special one if it's a molecular element. Okay, and then we would balance after that. And then if we have two ionic compounds, it's double replacement. Okay, we swap the metals and we form our two new ionic compounds. We drop and swap them on the other side and then balance. All right, I give that to you guys. I don't want you to use it for long. Okay, so I'm going to print it for you and give it to you here, but it's a bit of a crutch. Okay, and the purpose of a crutch is not to be permanent, but to allow you to walk until you're better. Okay. So it's here to allow you to walk until you're better, but don't expect that this is one of the things you'd be allowed to have with you on a unit exam. Okay, by the time we get there, I expect that you can just do this without the chart. The quiz tomorrow will probably just be on writing reactions with no prediction because we've only had one day of prediction. Actually, you know what? There's not going to be a quiz tomorrow. All right, well, let's look at 6 first. Okay. So on number 6, we've got a single replacement reaction occurring. Potassium is a metal, so it's going to swap out for iron. Okay, so iron will end up by itself. Potassium will end up with oxygen. Okay, this is a -2, this is a +1, so we got K2O as our, sorry, that doesn't look like a 2, K2O there. Now we got to balance the whole reaction. Okay, I would say I just have to come back over here and put a 2 in front of potassium, and it's good. Okay. 7. Okay, so on 7, I've got a double replacement reaction. Okay, I'm going to swap the metals so that magnesium ends up with sulfate and copper ends up with chlorine. Now, which copper was I using over here, 1 or 2? 2, okay, because this is a -2. So over here, I have to use copper 2 as well. So it's going to be CuCl2. This is a +2, that's a -2, so that compound is okay. Now we just need to balance. Okay, done. It was already balanced. Okay, and then for number 10, we got a trickier reaction here. This is a double replacement reaction. This is not, okay, this is cobalt, C(o). Okay, was that the confusion? Oh, okay, all right. So it's a double replacement reaction. Lead's going to end up with phosphate. Okay, I'm assuming it's going to need a number, but I could be wrong. Okay, and cobalt is going to end up with chlorine. Now, on this side, okay, since phosphate, is a -3, okay, this cobalt had to be a +2, so the 2 goes there. Lead's a 4, so we're going to have 3 and 4, so we'll have 3, 4. Okay, then you got to balance it from there.
Kevin,